So dear students, let us to continue the remaining part of electrostatic potential and capacitance. So let us to discuss about dielectrics and polarization. See, dielectrics are insulators, means non-conducting substances. They have no means or negligible number of charge carriers, so they will not take any part in the conduction. So in that, again, two types of molecules: polar molecules. A polar molecule is one in which the center of positive and negative charges are separated. Such molecules have a permanent dipole moment. An ionic molecule such as HCl or molecules of water are example of polar molecules. Non-polar molecules. A non-polar molecule is one, its center of positive and negative charges coincide. The molecule then has no permanent dipole moment. For example, oxygen and hydrogen molecules, which because of their symmetry have no dipole moment. So let us to discuss capacitors and their capacitance. See, in this figure there are two conductors. One is positively charged one, another one is negatively charged one. So what happens when these two conductors separated by small distance and the insulator which is introduced in between these two conductors? So the potential difference between these two conductors, let you can say V, and this potential difference V is proportional to charge Q, and the ratio charge to potential is constant, and the constant C, that's equal to Q by V, is called the capacitance of the capacitor. So, and this C is independent of Q and V. Remember, as Q changes, V also changes, but the ratio remains same. So hence this proportionality constant C is independent of Q and V. It depends upon the geometry or the dimension of the body. The capacitance C depends only on the geometrical configuration such as shape, size, separation. Cleared? So geometrical configuration of the system of two conductors and the medium separation between the conductors, means in between two conductors which dielectric material is filled, on that basis the capacitance of the capacitor depends. And capacitance is denoted by symbol C, and the SI unit of capacitor or capacitance of a capacitor is farad. That is 1 farad equal to 1 coulomb per volt or 1 coulomb upon 1 volt. The other common units are microfarad. 1 microfarad means 10 raised to minus 6 farad. Nanofarad, 1 nanofarad means 10 raised to minus 9 farad. 1 picofarad means 10 raised to minus 12 farad. A capacitor with fixed capacitance is symbolically shown in this figure. So this one is the circuit symbol of capacitor. Cleared? Okay. Next we go to dielectric strength of a dielectric medium. See, we have already discussed dielectrics are non-conducting substances. They will not take any part in the conduction. So dielectrics are insulators. But what happens, for every dielectric, it has its own strength. If the field is more, means beyond the strength, so what happens, the dielectric R behaves like a conductor, and up to what value of electric field that can withstand or that can tolerate dielectric material medium, and that one is called as the dielectric strength or strength of dielectric. Okay, this is the some explanation part. When a dielectric is placed in a very high field means here electric field, the outer electrons get detached from their parent atoms. They become free electron. The dielectric under this condition behaves like a conductor. Charges are conducted through the dielectric. This phenomenon is known as dielectric breakdown. Okay, so if the question asked what is dielectric strength, the maximum electric field that a dielectric medium can withstand without breakdown is its dielectric strength. Dielectric strength for air, it is about 3 into 10 raised to 6 volt per meter. For a separation between conductors of the order 1 centimeter or so, this field corresponds to a potential difference of 3 into 10 raised to 4 volt between the conductors. Thus, a capacitor, to store a large amount of charge without leakage, its capacitance should be high enough so that the potential difference and hence the electric field do not exceed the breakdown limit. So let us to discuss the parallel plate capacitor. So in this figure, two parallel plates having cross-sectional area A each and D be the separation between two parallel plates, and the space between two parallel plates are filled with dielectric material medium. Let the dielectric material having the dielectric constant epsilon r. See the brief explanation. X and Y are the two parallel plates and each plate having cross-sectional area A separated by distance D and containing a dielectric medium of absolute permittivity epsilon. Let the plate X is given positive charge whereas Y earthed. The electric field E between the two plates is uniform except at edges. The potential difference between the two plates is V. Then we can write the electric field E equal to V by D. You can call this as equation number 1. Next, if rho or sigma is the surface charge density, then the electric field in terms of surface charge density we can write as sigma divided by epsilon, and sigma is surface charge density, means charge per unit area is sigma. So in place of sigma we can write Q by A. So finally we can write E as Q divided by A epsilon. So you can call this as equation number 2. So we have already known the relation between electric field and electric potential. So potential difference per unit length itself is the electric field. So electric field we can write as V divided by D, where V is the potential difference between two plates and D is the separation between two plates. So we can write V by D equal to Q upon A epsilon. So now by simplifying this, so we can write Q as A epsilon V upon D. You can call this as equation number 3. From the definition of capacitance, C equal to Q by V. So now by substituting the value of Q from the above equation as A epsilon V upon D, so C equal to A epsilon V upon V D. So V get cancelled. So epsilon into A upon D. So this is the final expression of capacitance of parallel plate capacitor. So we have already known epsilon as epsilon naught into epsilon R. So we can write capacitance C equal to epsilon naught into epsilon R into A upon D. And one more thing you have to remember, if air is the medium between two plates, then the capacitance of air capacitor as epsilon naught A divided by D. So this is the final expression for capacitance of parallel plate capacitor. Is it clear? Okay. So check it properly, and here in this expression you have to remember the field between two plates is uniform and it is potential difference upon distance. And also we can write field as sigma divided by epsilon. So sigma as charge by area, and by equating these two, so we'll get Q as A into epsilon V divided by D, and by definition C as Q by V. So by substituting the value of Q and by simplifying it, we'll get epsilon A upon D, that is C equal to epsilon A divided by D. Okay, it is very important expression. Thank you.